Open up my voice. Okay, so let's talk about something related to homework 3. Actually, you got a good point about the homework 3 instruction discrepancy, which is about even instruction in your virtual machines, which I just get some modifications. Uh, Simply in my implementation, I get everything accurately and correctly, but not necessarily in the instructions. Sometimes it says overlook something. So again, I just got an update. So I will soon send out the announcement to let everybody know. So we got a even instruction update. And as you can see right here. So now I think it's a very directly reflected to the implementation of even instruction execution in your virtual machine, which is you are simply going to decide whether that number is even or not. All right. Any other question I may have? I think now is 100% accurately reflected to your virtual machine. All right. Yes. Yeah. Why should I update? Let me ask you this question. So before I creating this instruction, I got my pseudocode. I got my expected code is running correctly. So sometimes I just overlook it. As you may know, we got 50 pages instructions. I have to read every single things. Sometimes I just overlook a little details. All right. It's very good somebody is catching this problem. Yes.
Override this complex with the even instruction output.
Yes.
In the announcement, you said that we should implement it.
So that's something I'm basically mistakenly. So previously, somebody mentioning about discrepancy happening from the previous one and current one. So we have two different implementation in the instructions. Now so previously I consistent it, but never realized something went wrong. So now I realized something went wrong, so I corrected. So I will soon send up the email and basically deleting whatever the wrong email or the announcement I got. So sorry for the mistake and sorry for the confusion, actually. Any other question I may have? Anything? Again, I'm doing my best job to help you, okay? And of course, now I simply released your discussion platform. Great. All right. But for that, you only got, I believe, is 1 week. Yeah, 1 week or more than 1 week to finish this discussion platform. It means you could only earn up about 2,800 maximum point from now on. If you haven't reached to the maximum points, you should find a way to do so. Okay. And of course, you also got your attendance grade as well. If you attended perfectly, you should got 1 for the grading. If not, something is wrong. Okay. So for the finals, we actually not going to utilize this UCF here because UCF here simply will pause before the final week, and your grading will basically covers all the attendance rate just before the final exam. And what we are going to do to ensure you are here is basically our TAs will standing right there at the 2 doors. And once you go outside, you'll simply show your name, your ID card with the submission. They simply confirm you have submit your final exam and you are free to leave. So it simply prevents somebody is not submitting and simply go outside using some plagiarism techniques and resume on the finals, which is not my intention. Okay. Anything about homework 3? You got your grade. Anything related to now? Any complaints or etc.? Yes, yes, no, no, yes. You don't what? Okay, then that's your complaint. I have no such resources to resolve it. So you have to work hard on homework 4. That's the thing. Any other things I have? Yes.
I received a comment saying that XLC, not all the errors were handled, but specifically saying what the issue is. So I'm not sure when to.
Lex.c. So Lex.c is handling what errors? I know. Yes. Mm-hmm. Mm-hmm. Number too long, identifier too long, and invalid symbols. So 3 errors. So are you supporting all 3 errors to output in the symbol 1? It should. You're pretty sure? Or we can talk about this one in our office hours if you wish. Okay. If you do wish to like debugging what exactly the errors happening in your homework 3, come to my office hours. Any other question I may have? And if not, let's start our lecture. So for now, we only have left 3 lectures. So almost the end, okay? So again, for your finals, you are going to have 50 questions, 50 questions, okay? The exam is spanning over 2 hours and 15 minutes, okay? So again, go practice the quizzes I have given to you, and let me simply check how many of you have practiced on that. Oh, nice, 3. Okay. We got 180 different 180 students, but only got 3 to practice on that. No, it is purely your job. It's purely your responsibility. I have no judgment on that. Whether you practice, whether not. So simply, I would not judge. But final exam will coming from those questions. Could be some new, could be something that is kind of using a different phrase, but the concept is here. Okay. Any other question that may have? You have one?
Because I have a class right after this one that's having a final that's like 2 hours, even though the class is a 50-minute lecture time. What do I do if there's a possible conflict?
It should not be possible conflicts. You have to check the other class exam time. So you can simply go to Google and to double check on that. So let me just give you something. So UCF final exam schedule. You simply go to that, check on that.
Okay.
All right. So I believe the university has done its job to not have any conflicts between classes. All right. Any other things I may need to know? Or that's it? Okay. Again, so by this, if you do have any questions related to your homework 3, instead of sending me an email to tell me I'm simply dislike my homework 3, you have to come to my office hours to discuss it. So we will judge it fairly. I'm giving you a chance to raise your voice and send it to me. Okay. If you simply have something related to the implementation, you have questions, you should come to me in person or visit me by Zoom office. But you should not simply sending me an email. Simply, I would just simply disregard any email about like pointer adjustment, grade adjustment. All right. Okay, so let's coming back to what we have talked about in the PSW on this slides, and hopefully we can finish all the slides and land into a different lecture slides so that we can have a better discussion about multi-programming. Okay, so here we have the slides which is including all the PSW flags or interrupter flags. Simply, I'm just checking. So let me refresh your memory. What is OV? Overflow, MP. What's that? Who is saying what's the memory something? Yes. Memory protection, PI. Privileged instruction, TI. What's that? Timer interrupt, IO. IO is IO. SVC. Come on. Open up your notes, find a word. What is that? What is it? System call. We should have a better name. What's that? Got it. Supervisor call. Okay. Now you got it. So we have everything here. And let me ask you the second question is, what are the hardware interrupt flags? Yes. IO is one. Do we have another? What's that? Traps? Do we have traps flag here? You only have 6 different options. Yes. You. What? Memory protection is hardware flag? Yes. Timer it is. We have timer and IO are hardware interrupts, and all the others should be software interrupt. But once again, what is the spontaneous interrupt raised by your program? Simply think, so spontaneous one is I want, so your program is saying to the operating system, I want to interrupt. I want some kind of interrupt. Yes. Supervisor call. Now you got it. So now I think we have built a very robust interrupt system. There's one more refinement we want to bring to this, like the interruption implementations. So up to now, our design, which is conceptually a design that had a single entry for the entire interrupt flags. We just simply call it generic interrupt handler. So which is the CPU jumps to one single new PC. So that's the only single generic handler we have. So on any interrupt and an OS operating system or OS code simply would examine the flag to figure out, what happened. So is that something happened? I can go to the new PC and find something related to that. So it means in your entire code in the memory protection area, you have the error interrupt flag or interrupt handler has a huge chunk of switch segment. Just say, okay, I got a word for 1, for 2, for 3. I have to find it in your memory protection areas. Your operating system is doing the job for you. But so it means we could have a little bit overhead. Overhead means we have to do some calculations. The operating system interrupt handler has to check, was it OV? Was it some MP? Was it PI? Or was it some IO, SVC, or something else? And it simply branches appropriately routine for that case. And this task takes a lot of time. And the idea of what we have here on this slide, on the title, which is called interrupt vector, is here to cut off any analysis step by having a hardware directly jumping to that correct service routine, and depending on which interrupt occurred. So in other words, what we are going to do is partition the interrupt handler by the type at hardware level. Okay, got it? So, but the question is how? We know that we can partition it, but the question is how? How do we do that? We simply set up array. That's the only thing. We simply set an array of addresses in memory, and along basically analogies what we have learned about SCVT. SCVT is a table. which we handle all kinds of SCV calls to go by going into that table, we know some kind of things. But it's now we are serving this as interrupts. So we simply call this one as interrupt vector table. So each type of interrupt will have its own designated slot or vector in this table, which contains the address of its handler. So for example, let's say a vector 0, so this vector at index 0 might be the address for overflow handler, 1 for memory protection handler, 2 for privilege instruction interrupt handler, 3 for timer interrupt handler, 4 for IO interrupt handler, 5 for SVC interrupt handler. Okay, that's the idea. So with that in place, when an interrupt occurs, the CPU doesn't simply just go to like generic new PC. Instead, it will go figure out the interrupt flag is set, and it uses that index into that interrupt vector and load appropriate address for that handler. So if an IO interrupt is signaled, the CPU will automatically fetch the address from, let's say, slot 4, slot 3, or slot 1. So that's the idea. Then the key takeaway from this slide is that the interrupt vector is essentially a mechanism to achieve fast direct switching from the correct interrupt service routines. It's an array of handler addresses indexed by the interrupt type. So in this way, the decision of what to do for its interrupt is made the hardware immediately, rather than some software entering the generic handlers and it's doing its job. So to connect this idea back to the modern real-life CPU architectures, we actually have a lot of architecture following this implementation. We actually have x84 or x86. x86 is what? Let me ask you. What? So what's that? You don't know about x86? It's a CPU architecture. And what is the manufacturer for it? The major manufacturer for this CPU? What's that? Intel, yes. ARM is also implementing this one. Who is implementing this one? Who is the main? Apple? Apple is the major one. And now we have another competition coming up, which is called Qualcomm. And Qualcomm is the major manufacturer for the ARM processor for a decade, actually. Whatever you are using your, like, let's say, your iPhone. Your iPhone chip is already being ARM architecture for a lot of time, longer than that. Apple is using its ARM processor in the current Mac OS or Mac computers, but in the ancient time, they are using Intel's, but they simply set to the ARM. And how about the Android? Whatever the Android phones you are using right now is possibly produced by Qualcomm. So Qualcomm is doing this kind of ARM architecture for a long time. So why they want to use one? So it's basically using the interrupt tables for efficiency and organizations. Got it? So now, for each type of interrupt, there will be a corresponding entry in the array stored in memory. So the interrupt vector table. So what do we have here on this slide? Simply refer this table as IHV, interrupt handler vector. So instead of transferring the control to a single generic interrupt handler, then checking on the flags whether it's OV or something, or the CPU simply will specify the exact element in the interrupt vector that corresponds to the interrupt that occurred. For example, if a privilege instruction trapped occurred, so the CPU simply will set the PI flags to 1 and its position, so let's say index 2, then directly go to that vector entry 2 and to fetch that the PI, the privileged instructions, error handler or interrupt handler. So in effect, each interrupt types service routine becomes a separate program. Let's say could be a function. A starting address for each such routine is kept into a vector table. So when the interrupt happens, the hardware does so something like PC equal to interrupt vector IHV square bracket n, and where n is the index for the interrupt type. So at this time, the correct routine is automatically executed rather than we go to the generic one. So how we can implement that is what we are showing here. Yes, question. Why you are picturing this? All the slides is being uploaded. Okay, no problem. So whenever you have something that you want to picture, of course, go ahead. Okay, so now we're coming back to the pseudocode we have landing on. We will have consistently improving from this overall this throughout these lectures. Now we have an array. So this array is simply basically the IHV we're talking about, this interrupt vector table we're talking about. So now we have setting up everything correctly. 0, index 0, 1, 2, 3, 5. So that will be all the interrupt flags. In total, there are 6 different flags. And we'll have the content. So even though we have saying is OV, so simply is an address that leading to the overflow interrupt handler program that index for that. So based on this idea, we simply modify the pseudocode to be whenever we go to find some errors, we simply go to the PC equal to IHV0. That's for OV. IHV1, MP, IHV2 for PI, etc. Simply modify that. So nothing really special here, simply modifying the IHV. So change the new PC to IHV. Now, throughout this discussion, we have like simply focused on the interrupts and the mode bits in the PSW. But once we recall the PSW, so PSW often have something like holding the conditional codes, which is also called CC as well. So conditional codes are some Boolean flags that result from arithmetics or logical operations. So we have, in fact, been using this overflow flag, the OV, as one, excuse me. So one conditional code specializing for the trapping, but there are others just purely for the program logic for the automatic result. So we have learned about this in our lecture 1. We have a conditional flag, a conditional code. What is it? What are they actually? Yes. A Z flag, yes, Z flag is for what? Is an abbreviation of what? What? Zero flag, great. So zero flag, which is set to be 1 if the result is 0. Last computation was 0. It will be set to be 0 otherwise. Many machines basically include at least the Z flag because it's used for implementation of high-level construct like loops or if statements, while statements, etc. So it's basically meaning like branch if equal to 0. So we'll use that flag. So the PSW will also include not just the interrupt flags mode and mode. They also have some bits with conditional codes. Up to now, our simple machine here, simple machine design, didn't explicitly discuss them, but alongside with OV, but here we acknowledge them. The conditional codes exist in the PSW. But now, simply for the completeness, let's go to the von Neumann machine we have been familiar with. How we can add some like Z flag in the implementations. And we actually have some Z flag around here. Simply, you can see whenever we do some automatics in the ALU produces some OV, which is also a conditional code. But Without this conditional code, we simply installed this kind of things into another ALU. This ALU simply check whether this result is 0 or not. Simply, as you can see, you simply implement that, compare that. If something is equal to 0, simply set the Z flag to be 1. So that is the implementation we are adding to here. Now, we know that. Now we have explicitly showing that PSW layout, including all the CC code we have discussed in our lecture 1. That's basically connecting our memory back to lecture 1. What do we have here? G, Z, and L. What is Z? We said it, 0 flag. G, greater flag, less L. So basically having those three flags, the G, Z, L, we can effectively tell if a number is positive, a 0, or negative. So this is very useful for making the decision. For example, let's say a comparing or subtract, or those flags will simply tell us the relation between those two values. This is a bit of unusual name. So if you have encountered some unusual name in your life or in real life examples, it could be some architecture is using some N, so a letter N for negative, and for the L instead of L for less, or some maybe carry a flag C, which is for unsigned arithmetics. So there could be a lot of different variation of conditional code, all right? But the idea is the same. We have something related to conditional code. Now, this is the last slide we have for this lecture. We simply conclude with a broader concept that ties into why we want added a timer interrupt. So why we want a TI interrupt or interrupt flag in this implementation of PSW. So now it's related to that to a concept of multi-programming. So multi-programming is essentially a practice by having multiple programs, not really programs anymore. We are talking about processes. So loaded into the memories, sharing the CPU by taking turns. And what we have here on this slide is basically defined as allowing 2 or more program to residue in the memory at the same time. And why this timer critical for this task for the multi-programming is that to run the multiple programs, let's simply call them as P1 and P2. Okay, so again, we have to make a big disclaimer is that the setting of the entire lecture, entire course is that we are only working on a single CPU. That single CPU is only having a single core with single thread. It only can produce working on this task one at a time. Okay, this is a big disclaimer. It's not unlike what we have here in the modern computers. Your computer CPU could have multiple cores, 8 cores, even 16 cores, even 64 different cores, and even have 128 different threads for execution. Not that time. We are studying the basics, the fundamentals, which is one CPU, one core, one thread for the task. Okay, we could have multiple threads, but one core is the same, one at a time, okay? Now, what we call here, we have P1 and P2, we have executing them simultaneously, quote, simultaneously from a user perspective. The OS simply cannot just let one, let's say, a process run to completion and start another. Simply is running one program and one at a time. Is that possible? It is possible, but it's sometimes wasting time. Let's talk about it, it's wasting time. So for example, so one, it means one program, the process could simply hog the CPU while the other simply waits indefinitely. For example, if a P1 is waiting for IO completions, it could be waiting for a lot of 3 seconds or 5 seconds for that things. Do we still waiting on him to completing the IO? Your CPU simply sitting in idle. nothing has been really executed. You're simply waiting on the I/O. Why don't we simply switch to another program or another process for the execution? So that's the idea we're bringing up for the multi-executions. And so it basically means the PI, for example, P1 runs for a few milliseconds, then we switch back to P2, runs a few milliseconds, then coming back and forth. So in other words, none of the programs will hog the CPU resources for a very long time. We simply switch them back and forth to make sure that it basically creates an illusion for you as the one who write a programs and running in this this CPU design simply think they are running in parallel. Okay, even though we have one single CPU, we still can run them in conceptually parallel. Okay, now it's basically we're implementing this alternative execution by using a timer interrupt. So the OS simply will start the PI, also for example, P1 to then set up timer, then the P1's timer is sliced up, we simply switch to P2, set up timer. If P2 finishes a job or the timer is up, save a state, switching back to P1 again. So this is switching back and forth again. Now, so again, it's when we coming back to this slide, we have to talk about what is the process so related to what we have talked about here. And I'm always consistently about using this is a process we're talking about. Then what is process? Yes. Programming execution, actually we have it here defining right on the slides, so you can directly read it. So it's a programming execution. So in order to implement multi-programming, the operating system will basically introduce an abstraction of a process, so which includes not just the program's code or data, but it's just the current state, such as the value of in the register, the program counter, the stack pointer, and etc. And each program will have talk of P1 and P2. P1 and P2 becomes a process with its own state. The OS, the operating system on a timer interrupt will perform the context switching from one process to another, meaning simply we are storing some state of P1, then switching back to P2, and resume the state of P2. Then if the P2 finishes, we simply save that state back to P1 again. Yes. Is that thread, which we will discuss in next lecture. Okay, don't worry about it. So what do we have here on the slide? Simply we summarize everything. Summarize everything. We have the multi-programming basically uses a timer interrupt to allow multiple processes to share the CPU. And each process is a program in execution with its own context. The OS uses timer interrupts to periodically regain control and switch among processes, and giving the effect they are running concurrently. Okay? So this is the fundamental capability of modern operating systems. Now we have covered the low-level mechanisms. We have interrupts, the mode bit, the stack for the context saving, and the interrupt flex when it's making it possible. So now we have acknowledged this understanding. Okay, yes. 2 slides. Original one could be performing a different task for now. So that is why we have additional ALU for simplicity, for modularity. Why we have a different ALU and this design is that we have to have some numbers to compare with. A Z flag is comparing to 0, right? So it's similar to our even instructions. It is comparing to a 0 again. Is divided by 2 is fully divisible by 2 or not? Okay. All right. Good question. Now coming to this process concept. what we have here is simply we're going to introduce the idea of some like TCP, the process PCB, which we going to review, and TCP thread control blocks, which is we have never familiar with. So that's the introduction of TCP. And of course, these are all the cornerstone of operating systems. All right. So when we run just a single program on CPU, we often encountered an efficiency because CPU ends up on waiting around. So imagine a scenario where your program needs data from the disk. This is I/O operations. So for this data, the CPU sits in idle, effectively wasting the valuable processing time. So why is that? So we have to consider the architecture of the current modern systems of the computer. What do we have here? We have different storage. How many storage we have talked about in this class? How many types of the different storage we have talked about in this class? Yes. No, not this one. We're talking about physical connection between your CPU to different components. In your typical laptop, how many components you should have in order to operate? What's that? What? 3? What are they? Memory? SSD. Oh, okay. Now you're getting modern. So SSD, you don't even counting at the hard drive is a drive. Okay. Last one. I'm waiting. What's RAM is memory? Come on. CPU is the major one we're talking about. It's not storage. And what? MDR? MDR is a part of the process, the CPU processing. But it's having a generic name for that. Yes. Hard drive is same as SSD. It's the same type. Yes. Cache? Cache is what? Cache is not a type of memory. But what we talk about more closer to the CPU, we have a generic name for the storage closer to the CPU. Yes.
Oh,
Is that storage? What's that? Registers? Yes, it is registers. Yeah, 3 types: registers, memory, RAM, and lastly, hard drive. Okay, so 3 different types. Then about 3 different types, which one is the fastest? Register. Then coming to the next. Memory, and last one, hard drive. Okay, so these are 3 different types. They have different speeds, but why is it sharing the different speeds? Have you ever considered of that? Yes, distance is one factor. So of course, register is much closer to the CPU, the central processing unit. Then we have memory. Memory is sitting basically very close to the CPU, but never like close enough comparing to the registers. Then we have hard drive. Hard drive is far from the CPU. You have to connect some like SATA connection. If you have ever built a computer by yourself, we have SATA connections. That SATA connections is something that limited with its bandwidth, okay? But the bandwidth is its limitation with bandwidth. We still have different speed for the hard drive. If you consider that mechanism hard drive, we only have a disk spinning around inside the mechanism, and that unit is very kind of slow. But if you're having some kind of SSD, it's faster, but not fast enough to act as a memory. Okay, so we have this idea to concrete enough. We have to talk about timing. Whenever we're accessing something from the registers, the most likely we're just causing some like nanosecond or even less than a nanosecond, but for drastically speaking, less. making it into more dramatic. So let's say we have a register, we're accessing some materials from the registers. The register could causing, let's say, 1 second. And that 1 second will be something that we are considering, okay, we are making it very dramatic. Then we come into the memory. We're fetching something from the memory. How much time we could cost? Could be, let's say, 100 seconds. It's slower enough, but still bearable. 100 seconds, still bearable. But once you go to some hard drive to fetch some data, it could be causing 2 hours, let's say 2 hours. So it means whenever a program is halting, you're hogging the CPU's resources, just waiting for the I/O. Are you just simply waiting on the I/O implementation to finish its job? You are waiting like your CPU is sitting idle for 2 hours. Are you willing to sacrifice that? Not necessarily, no. So we should have completing more meaningful task just by sitting the CPU idle. Just to consider, you are the chef. You are preparing some dish. So while you are waiting the water to boil, you should have something else to do, right? So then you don't want your chef to do nothing while waiting. And so the multi-programming addresses this by allowing multiple programs to share the CPU. So one program waits, another can execute, so ensuring the CPU stays busy. Okay, we don't want it to idle. So essentially, it's like a chef is preparing the multiple dishes simultaneously. It's waiting on the water to boil. At the same time, it can fry something. While it's frying, they can saute something. Okay. So let's build further on the multi-programming. So now we understand the multi-programming simply boosts the CPU utilizations by having several programs load into the memory at once. So the core idea is to when the program initiate a very slow operation, such as disk management or disk I/O, the CPU doesn't sit in idle. Instead, the operating system quickly assign to another program, another process ready for the executions. So the interleaving of the tasks simply ensures the CPU stays productive and reduces idle times, and basically making it possible that we can have some structured way to handle this multiple running programs separately and effectively. That is why we introduced the concept of process. We have to understand the process first, which is programming execution. So once we have this idea concrete, then we come into this slide. So we know that a process is simply a programming execution. It means it's active, it's dynamic, it has its own life cycle. And think about the recipe. So if the recipe itself is just a static code, but the act of cooking itself is a process. So it's an asynchronous of so it basically it's activity, meaning it runs independently and it can progress on its own pace. So the operating system keeps track of each process throughout the data structure called PCB, process control block, and which PCB records everything that OS needs for manage the process, like the current state, the registers, the resources. So the processes move through different states during its lifetime. So a new process starts with a new state and etc. We will talk about those states in very detail. What we have here is just simply a definition. So what we have here, new, is simply whenever we create a new process, it's now in the ready queue, simply it is a new state. Then we come into the ready, it simply notify the CPU, okay, I'm available, I'm ready to execute. Then we have running state. Whatever the process is in the execution, it is in the running state. Waiting state is basically waiting something to be completed. We put into waiting state until it finished. You can put it into the ready queue again. A band is simply something that stops onto the error, such as overflow or something else. And will be something that is executing properly, and lastly, stop temporarily. So basically stop temporarily by the OS using the CPU, okay? Then sometimes it's just timer ticking. So this diagram, which is giving us an overview of all process states we just discussed and how they connected. So you have to visualize this. So we have each row is basically represents a state, and the arrow simply processes what kind of actions we can perform from moving one state to another state, which is not very clear here. Simply, you don't know what kind of action we are going to perform for each state transition. Now here it is the one we are talking about. We have new state, which is creating some new PCB that plays into the memory, and which means it is ready to execute. So it's in the ready queue, in the ready state. Whenever CPU is ready, simply dispatch it. Dispatch it means we can run it. So it's in the running state. Whenever a timer kick in, simply we are putting into the ready queue again, waiting on the other task to complete, then we coming back. So it's ready state, and once we coming back to the running state. Whenever we're waiting on the IO, simply we have put into the waiting queue, waiting on some IO completion. Once it's completed, put into ready queue, and whenever CPU is ready, put into running queue. And then we have the suspend system. Suspend is sometimes OS have to take control for something. So in this sense, we have to put into the suspend state and waiting it to complete, and once we resume. And lastly, we have the trap. Trap is whatever the errors we have encountered, we are going to the trap state. So abandon, abort it normally. And then we have EOP. Whenever we're facing some errors, OV, we simply go to the end. So end of the flag, simply go to the ending normally. So here, I think I can stop right here. All right, we can continue this lecture on Friday. So for whoever is attending on the Zoom, thank you for coming.